Hey guys, welcome to the video on acids and bases. Specifically, this video will talk about how to decide whether an acid is a strong acid or a weak acid based on its ARIO. So recall that when we look at an acid and we want to determine as to whether that acid is a strong acid or a weak acid, we really look at the conjugate base. If the conjugate base is stable, if the conjugate base is happy, if the conjugate base is weak, if the conjugate base is low in energy, then we have a conjugate base that came from a strong acid. So a strong acid will produce a weak and stable conjugate base. If you have a very weak acid, then it is going to produce a conjugate base that is very strong, that is very unstable, that is very reactive, is very high in energy. And so a weak acid gives us a strong conjugate base, or a conjugate base that is not stable. The four main things that we will look at in determining the strength of an acid are the atom, the resonance, the induction, and the orbital. And so remember, we have to do it in that order. So we're going to start off with the atom. That is the A in the ARIO. The atom that is directly attached to the proton that gets donated is important. And we look at the periodic table to see the trends. As we go across the periodic table from left to right, we get more and more acidic. And so if we think about the periodic table, we have boron, carbon, nitrogen, oxygen, and fluorine. Let's forget about the noble gases for right now. So as we go across the periodic table in this direction, fluorine is going to be the most acidic. And that is because the conjugate base of fluorine, once the H leaves, so we have HF, once the H leaves, we have this anion on fluorine, and fluorine, because it's most electronegative, can handle that charge. Now, if we look at the periodic table going down, we also increase acidity. So when we have fluorine versus chlorine versus bromine versus iodine, HI is actually the strongest acid, and that is because of size. So the larger the ion, so that I minus there, holds that charge because of the size. So the electrons are so much farther out away from the nucleus that gaining an electron is really not as big of a deal for iodine as it is for fluorine. So the trend in the periodic table in terms of atom, when you go from the left to the right, we increase acidity, and that's because of the electronegativity difference. And as you go down the periodic table, we also increase acidity, and that's because of size. Again, we look at the conjugate base and we look at the stability of the conjugate base. So moving across the periodic table, a carbon with a negative charge is going to be much less stable than an oxygen with a negative charge. In terms of resonance, if a compound has a resonance structure, it means that it is more stable. So if we look at the conjugate base of an acid and we see that it has a resonance structure, that means that it is more stable. If you look at ethanol, when we form the conjugate base, looks like this, and we cannot delocalize that charge anywhere. Whereas if we have acetic acid and we draw the conjugate base, we see very easily that those electrons can be delocalized in resonance. And we end up having a nice resonance structure that looks like this. And so that negative charge on the oxygen is actually shared between both this oxygen and this oxygen. And so that makes it more stable. So if the conjugate base is more stable, it came from a stronger acid. The induction effect is when we have through bond pulling of electrons. So we're looking at things that have a dipole. So if you have an electronegative atom that's attached to the compound far away from where the proton leaves, those electron withdrawing groups can pull electron density away from that developing negative charge of the conjugate base. For example, if we have acetic acid, here's acetic acid, and we already said this is a pretty strong acid because it has resonance, right, when we draw the conjugate base. However, if you also add these three electron withdrawing groups, we're going to also have some inductive effect where we're going to pull the electron density away from the developing negative charge on the conjugate base, in addition to having it delocalized in resonance. So anything that has an electron withdrawing group. And what we mean by electron withdrawing group are the atoms at the top and on the right of the periodic table. We have fluorine, chlorine, bromine, and iodine. And then we have oxygen, nitrogen, carbon, and boron. And so the electronegativity increases going across the periodic table, left to right, and going up the periodic table. So the more electronegative atoms are the ones that are going to be electron withdrawing. So an electron withdrawing group is one that is very electronegative next to one that's electropositive. And so we have unequal sharing. So we have that dipole and we're pulling electron density through. And so if you look here, you can see that a C bond is typically not polar, but once you add that fluorine, we're going to have this dipole pulling the electron density away. And note that the carbon here is more partial positive than the carbon here. So distance matters. So the electronegativity matters. The more electronegative is going to be the more electron withdrawing. So it's going to stabilize the conjugate base even more. And distance. So the closer it is, the more it's going to stabilize that conjugate base. And so that is the I in ARIO. And here's just an example. The pKa of acetic acid by itself with no electron withdrawing groups is 4.75. And we can see that the pKa decreases as we go across, where we have 3 electron withdrawing groups that are all pulling electron density away, and then when we have that conjugate base where there's a negative charge out here, then that is going to be stabilized. And the last one is the O, or the orbital. And here what we want to think about is that the shorter sp hybridized orbital is going to hold those electrons closer to the nucleus than the sp3 and or the sp2. And so you want to think about the sp hybridized carbon being able to stabilize that conjugate base better than the sp3 and the sp2. And so if we look at this molecule right here, if we draw the conjugate base, this is an sp hybridized carbanion, which is going to be more stable than over here. We have an sp2 hybridized carbanion. So the more S character, the more acidic. So the more S character, the more acidic. So a triple bond H versus a double bond H versus a single bond H. This is the most acidic, followed by these two, followed by these three. So the lone pair on an sp2 is not as close, so it is less stable. The lone pair on the sp is closer, so it is more stable. So the more acidic proton is the one on the triple bond. So in summary, we have ARIO. We have to do it in that order. The first thing we look at is the atom that the hydrogen is directly attached to. The more electronegative, the stronger the acid, the larger, the stronger the acid. So we go across the periodic table and down. Resonance, if a conjugate base has a resonance structure, then it will be more stable. And we can go back and look at the rules of resonance structures to figure out which conjugate base is the most stable based on the stability of those resonance structures. Inductive effect, if you have electronegative atoms located on the molecule away from the site where the proton is donated, that conjugate base will be stabilized with the electron withdrawing groups pulling electron density away from that conjugate base. And finally, the orbital, as the S character increases, the acidity increases. And so I hope this helps summarize acids and bases in terms of deciding which acids are strong and which acids are weak. And again, this ARIO is not 100% of the time, but it works much of the time. We do have to be careful if there's a charge on our molecule that kind of mixes things up a little bit. Certainly an oxygen that is a positive charge means it already has an extra proton. And so that would be more acidic than your typical oxygen. Okay, hope that helps. Don't forget to practice. Lots and lots of practice is required for us to really understand this method of identifying acids and bases. Good luck. There you have it, ARIO.